Section A1 is about sequences and series, and a lot of times you immediately kind of start thinking about arithmetic and geometric sequence and series, which is, we're going to get to that. But these are just more generically defined sequences and series. So I want to really focus on some patterns you're going to notice, and that's going to be things like even numbers, odd numbers, alternating sequences that go from plus to minus. When you have a fraction, when you don't, perfect squares. Those are some common things that you're going to see. And if you haven't really thought about how to define those, you're going to really definitely learn how to do it just from your work doing this section. So that's really kind of where this is going to go. So the first one we've got here, we have a series or sequence defined for us. Just a quick reminder, sequence is a list of numbers that follow a pattern. A series is the sum of that list of numbers, and it can be a list of a few numbers or it can go on forever. Those are both possibilities. Sequences, they go on forever. Sometimes we just look at pieces of the sequence, but they do go on forever. So it's defined as A sub n. This is common terminology. A means basically a term in the sequence. N is a way to number the term you're looking at. So if you saw the entire list, the first one's A1, next is A2, next is A3, and so on. And whatever we plug in for n here, if we're on the fifth term, to produce that, you put a 5 in for both of these. So this will be a whole number, because sometimes you'll see A sub 0 as the first term. Typically A sub 1 is the first term, and it really doesn't matter all that matters is how it defines the formula, and you'll mess with that a little bit throughout the chapter. So let's find the first 5 terms. To find the first one, we want A sub 1, which means we're plugging in 1 for n. So off to the side, I'll do it right here. Negative 1 to the first over 2 times 1. So whatever's here goes in for n in both spots. And minus 1. So negative 1 to the first is going to be negative 1. 2 times 1 is 2, minus 1 is 1. So this term is negative 1. And everything stays the same. We'll just change the n's to a 2 in this case. So that is a 2 and this one's a 2. Negative 1 squared becomes positive. So a negative to an even power makes it positive. So this is positive 1 on top. This will be 4 minus 1, so it'll be 3 on the bottom. Now after we do 3 of them, and you might have suspicions about what the pattern is, but after we do 3, you should see a clear pattern developing, and you may not need to go through all the math every single time. Do it if you need to. If you get the pattern, that's fine. You can continue on. It's probably going to be more helpful as you define your own, because you're going to start with the answers and get back to a formula on the homework as well. So if you can kind of see where the pattern's going, that might kind of help you find the formulas later. So I'm going to do one more this way. Put in 3 for n. Negative 1 cubed will be negative 1 again. 2 times 3 is 6, minus 1 is 5. So if we look at what's going on, and honestly it might be good to look at this piece to kind of follow the pattern, because they're fractions. This wasn't a fraction because it was divided by 1, but basically your outcome is a fraction each time. Signs are alternating between positive and negative. And on the numerator it's always 1, and the denominator is going through the odd numbers. So I could go ahead and predict, and it'd be correct, that this will be positive 1 over 7. And the next one, the last one here, in this case, will be back to being negative, 1 on top, and now 9 on the bottom. And you can plug in 4 and plug in 5 and verify that, but that is the pattern, and that'll work. Now, as usual, you've done it one way. Let's reverse the process, start at the result of the last example, and go back to the formula. So we've got 3, negative 5, 7, 9. Before you start diving in here, start looking for any patterns you could use words to describe. Right away, I'm seeing that the signs are switching back and forth. The term for that is alternating sequence. And the way to make that happen is to take negative 1 and raise it to a power. Even powers make it positive, odd powers make it negative. So that keeps your sign going back and forth. And something else I'm noticing, these are all odd numbers. If you don't know how to define an even and odd number, you're going to know after this section, because you'll just stumble into it if nothing else. So we'll talk about definitions of even and odd. And the only other thing really that stands out to me is this has to start at 3. So that's the three rules I need to play by. I need an alternating sequence, which means the -1 to the n is going to show up. And it's going to be the odd numbers. It's going to start at 3. So while we're talking about odd numbers, if you've never thought about a definition, they're always one more than the even numbers. And the even numbers are just 2 times n, where n can be any integer. An even number can be divided by 2. So to create an even number, you reverse that process. Take any number multiplied by 2, it produces an even number. So the definition of even is 2n. Definition of odd is 2n plus 1. Now, an alternate to that is 2n minus 1, or really 2n minus any odd number. But really, depending on where you want to start, that helps you figure out which one of these to use. So kind of looking ahead, if I want n to be the first number I plug in, I want to say a sub 1. Well, if I put in 1 here, 2 times 1 plus 1 is 3. If I put in 1 here, it's going to be 2 times 1, which is 2, minus 1, so 1. So if I want this thing to start at 3, probably want to go with this definition for an odd number. So I want it to alternate. I want it to have odd numbers in it. So I'm feeling pretty good about -1 to the n times 2n plus 1. Let's just verify and let's see if that checks out. So if I put in 1 for n, and if you're defining the formula, you don't really want a 1 there, you want a little n that matches these n's. So a term for any given point in the sequence, plug in this value for n here and here. So if I did want a sub 1, well, that would be -1 to the first times 2 times 1 plus 1. So that would come out to be -1 times 3, which would be -3. Now, not too bad, but I needed this to be a positive 3, so it's the opposite sign from what I wanted. Really, all you need to do is just change what power you're raising this thing to. Because when I raised it to the first power, it stayed negative. So I can just do this little trick, n plus 1 right there. Now that changes it to 1 plus 1, so -1 squared is back to being positive. And then +1 times 3 is 3, so we're good to go. And you can check this for the second, third, fourth term in the sequence, make sure it checks out. But that is it. That is your formula. So again, look for those key little details to begin with, and you'll start to get used to what those look like. Alternating sequences have this part, odd numbers, that's the definition of odd right there. Example 3, I want to start the same way. I want to look for any patterns that are showing up. So one thing right away, I'm noticing these are all fractions. So that's going to have to be kind of built in. The formula is going to have to be a fraction. Let's look at the numerators and denominators separately. So the numerators, they look kind of like special numbers. They are perfect squares each time. So they're squares, that's the way I'll word that. Other things to be on the lookout for are factorials. Those will show up in these quite a bit. Factorials is things like 1, 1 times 2, which is 2, 1 times 2 times 3, which is 6, 1 times 2 times 3 times 4, which is 24, and so on. That's factorials. As far as your denominators go, they're just counting, basically, counting up by 1. But they do start at 3. So we're just going to continuously count by 1, so basically just n. But I need to make sure it begins at the right spot. I need it to start with 3 and then count up from there. So let's start engineering our formula. So for any given term, it's going to be a fraction. The top number needs to be something squared. So now I'm going to start with kind of a base here and build off of it. And we'll see what happens and test it out and then refine this. But I know I'm seeing squares on top, and I know I'm seeing numbers that are just counting on the bottom. So let's kind of test out a sub 1 and see what happens here. All right, well, if I plug in 1 here, 1 squared is 1, and just 1 on the bottom is 1. But I want it to start at 4/3, so that's not quite right. I really want this number to be 2 squared to get 4. So I'm going to refine that a little bit, and we'll say, all right, let's try n plus 1 squared. It seems like that's going to probably hold, because when I plug in 2 for n, I'll get 3 squared, which is 9. When I put in 3 for the third term, I get 4 squared, which is 16. So that's looking pretty good. I'm feeling pretty good about that part. I also want this thing to count by 1, so I like the n, but but I want it to start at 3 instead of 1. So when I plug in 1, it starts at 1. Let's just add 2 more to that. And that's probably going to hold 2, because I plug in 2 here. This is now 4. Plug in 3 for the third term. It's now 5. So that seems to be holding, and I'm pretty happy with that formula. All right, recursive sequences. These are a little bit weird because you can't, when it's a sub n, we can easily find the 500th term of the sequence just instantly if we'd like to. Recursive is, you've got to generate the entire sequence in order. You want to find the 500th term, you've got to generate the 499 terms that came first. So in that way it's a little more awkward, but it's got a lot of uses in one of my favorite fields of chaos theory and procedural generation. If any of y'all do programming, it's a way to make computers create some pretty graphically taxing situations, nice scenery, things like that, but with very small amount of computer usage. So I'll leave it at all that. The terminology sometimes can be kind of a hurdle here. Let's just kind of walk through it. Once you see the pattern, you probably don't need to think too much about the terminology. You'll be able to just kind of get answers, plug them in, and go from there. So right in the first 5 terms of this sequence, all right, well, a sub 1 is 2. So the very first term, it starts with 2. That's key. We've got to know where to begin with these sequences. All right, a sub k plus 1. What that means is if I started with a sub 1, add 1 to that, that would be the second term. So let's kind of do it that way. A sub 1 here, add 1 more to it, would be a sub 2. That's going to rely on 2 times a sub 1, which is 2. We're going to add 3 to that, we're going to get 7. All right, now a sub 3, the next term. We already got the first term, we found the second, now we're to the third. A sub 3 would be the second term plus 1 more, which means you're going to do 2 times your second term, so that would be 7 plus 3. And the pattern is just whatever you have so far, whatever term you're on, you plug that in for a sub k, and that's how you generate the next one. So that's probably an easier way to think about it. That's how most people do it. In this case, that's going to be 17. So to get a sub 4, now it's going to be 2 times your answer there, 17 plus 3. So it's 37. And you will see some patterns unfold here. I'll do one more. So I believe that was what I was asked to do, the first 5 terms. Yes. So we already had 1. So 2 times the answer we just got, which is 37, plus 3 more. And that's going to be 74, 77. So you're definitely seeing a pattern unfold here. If you look at the differences, difference of 5, then 10, then 20, then 40, you could use that and not even have to generate this way. You could say, all right, well, the next difference is going to be 80, so 157 is the next one. And then 160 would be the difference to the next one, and so on. So you can think of it that way. You can go back and redefine these things as a sub n equals, but really you got to generate them first before you're able to do that.